So we are going to start section 11.6, finish it pretty quickly, which is conditional probability. Okay. So thinking of this probability without replacement, this second bit changed because I introduced that extra condition. I've used up an envelope, so the second event depends on the first one occurring. Okay, so when we calculate probabilities, without replacement, the probability of the second event depended on the first one occurring, or depends on the first one occurring. Okay, so in general, the probability of event E2 occurring, given that event E1 has happened or will happen, is called a conditional probability. And is written as follows. So you have the probability, you want event E2 to occur, but you want to state given E1 has happened. So this bar indicates this condition has been set for me. Okay. So this is red. Oh, be helpful if I made something that made sense. This is red. The probability of E2 given E1. Okay. Best thing we can really do, it's just going to be a ton of examples, and that's about all we're going to do for this section. So let's try one out. We're given a bunch of shapes. So I've got a circle, I've got a triangle, I've got a square, I've got a second square, I've got another circle, another triangle, and one more circle. So a bunch of shapes going on. And inside each of these shapes is a number. So 1, 2, 3, 4, 5, 6, 7. So 2 ways to classify these different shapes going on. So each figure has an equal chance of being picked, just to keep things simple. Doesn't matter if one shape is bigger than another, they all are going to have exactly the same chance of being drawn. So we want to assume each figure is equally likely to be selected at random. We want to determine the probability of selecting first a circle given an odd number was selected. Okay. So basically right off the bat, anything that has an even number, it's gone from my pool. I've narrowed down my possibilities. So we're assuming an odd number was selected. So it narrows our choices to the following. And I'm going to copy and paste every single shape. An odd number was selected. So this one's gone, and this one's gone. I now have 4 choices remaining. So I've narrowed this down. I now have a number out of 4 as my chance of getting a circle. And from these, I want to select a circle. So I have 1, 2, 3 out of 4 chances to get a circle. So here, 3 of 4 are circles. So ultimately, the probability of getting a circle, given an odd number was selected, is 3 out of 4. Okay. Instead of originally, I had a 3 in 7 chance of getting a circle. Because I have just an odd number now, I know an odd was selected, I have a 3 out of 4 chance that it was a circle. Okay. So this is the idea. You start with this gigantic pool of stuff. You give some type of condition, narrows your selection down. From what remains, how many fit that criteria? Okay. So let's try a second one. Let's figure out the probability an odd number was selected, or determine the probability of selecting an odd number given that a circle was selected. Okay. So now I get to ignore everything that's not a circle. Those are my only options now. So since a circle was selected, our choices are as follows. I'm going to copy and paste all of my pictures again. But a circle was selected, so all those shapes are gone. But since a circle was selected, every single one remaining is an odd number. So all these remaining choices are odd. So our probability of getting an odd number given a circle was selected is you have a 3 out of 3 chance of getting an odd number. Okay. So this is going to be the idea of what we need to do every single time. So I'll give you a formula, but ultimately, again, you're going to be working with just specific examples. You want to narrow down your pool, changes that denominator. Okay. So here, for any 2 events, which we'll call E1 and E2, the conditional probability which is the probability of event E2 given that event E1 has occurred, is as follows. It's the number of events E1 and E2 have in common divided by the number of events in E1. Okay. So I'm going to go back to this previous example just to kind of see this. We'll do this one. We're looking at the number of events of E1 and E2. So basically, from this pool, what are the number of possibilities that a number is a circle and odd? That would be 1, 2, 3. So you have 3 possibilities going in that numerator. For the denominator, it's the number of events for that condition. So we had 1, 2, 3, 4 numbers that are odd, which is why there's a 4 in the denominator. So that's all this stands for. But I will go ahead and write that here. So this is how we find our conditional probability. where n of E1 and E2 is going to stand for the number of sample points common to E1 and E2. And n of E1 is the number of sample points in E1. Okay. So it's taken our event and it's changed our denominator. So kind of looking back up here, if I just look at the probability of getting a circle, I have 1, 2, 3 out of 7 chance of getting a circle. But by adding that condition of being odd, I've narrowed down my denominator to 4 possibilities instead. Okay. So I just have more examples, 2 more examples really, and that's it for that section. So I will likely also start 11.7 today. So this week we can hopefully finish up all of chapter 11, stay on track with our schedule. So let's go through another example. It's going to deal with some coffee. And this is the kind of stuff that you're probably going to be creating for your analysis. So the following results of a coffee taste test are given below. So we've got people that prefer Dunkin', people that prefer Starbucks, and then we'll calculate some totals. So they did one of 2 things, and they classified this by age. If my line wants to go. So for simplicity, I'm going to just write kids. So this is under 18. Sorry if you're under 18, I'm calling you a kid. And then we have adults, which we're classifying as 18 plus. And then we'll calculate those totals too. So you might have stuff like this in your probability analysis, which is that second part. So ultimately, you can create a table based on some demographics over here, and you can calculate probabilities that they like this given that they're in this age group. They like this given their income. Okay. So filling everything out, this is all given to us. 60 kids under 18 prefer Dunkin', 40 prefer Starbucks. So kind of adding that up, in total, we have 100 kids that were surveyed. For adults, 50 preferred Dunkin', 75 preferred Starbucks. So they surveyed 125 adults in total, and you add these together. Okay. Now you can also add down the line. So 60 and 50, 110 people preferred Dunkin'. 40 and 75, that tells us 115 people preferred Starbucks. Okay. And if you add these together, that means 225 people were surveyed. Likewise, if you add these together, 225 people completed the survey. Okay. So based on this chart, we're basically going to pick an individual at random. And then we're going to calculate a ton of probabilities. So if one of these individuals is selected at random, we're going to determine the probability that the individual selected first prefers Starbucks. Okay. So I have no conditions set. I'm just picking the person. What's the chance they like Starbucks? Well, 115 people out of 225 like Starbucks. So 115 out of 225 prefer Starbucks. So the probability the person likes Starbucks is exactly that, 115 out of 225. And if you want to condense it, you can. They're all divisible by 5. So divide top and bottom by 5. And I've already done it. So this gives you 23 out of 45. Okay. Now, let's determine the probability the individual selected is an adult. So going back to our table, 125 adults were surveyed out of 225. So the probability of an adult is 125 out of 225. And again, both divisible by 5, so divide top and bottom by that. You end up with 25 out of 45. But you can keep going. Both still end in a 5, so they are divisible by 5. So your simplest probability is 5 out of 9. Okay. Now let's try some conditional probabilities. We'll do quite a few of them. We want to determine the probability the individual selected prefers Starbucks given a kid was selected. Okay. I already know the probability of someone preferring Starbucks. It's this right here. But now I've added this extra condition. So I'm narrowing it down to only working with this kid row. I know a kid was selected. So instead of dealing with the whole population, I'm dealing with 100 kids. 40 of them like Starbucks. So really, it's going to be 40 over 100. Okay. But kind of going back to this formula so you can see the connection. The probability the person likes Starbucks, given they're a kid, is equal to the number of people that like Starbucks and are a kid divided by that condition, so the number of kids that were selected. So in total, 100 kids participated in the survey. Back up here. From those kids, 40 of them like Starbucks. So this conditional probability is 40 out of 100. I can squeeze this in up here. And then again, this does simplify. I will do the most I can. They're both divisible by 20. So this is a 2 out of 5 chance. They prefer Starbucks. Okay. Let's try 2 more. We want the probability the individual is a kid given they prefer Dunkin'. Okay. Before I go back up to the chart, I'm going to set this up. We want the probability of a kid given the condition is they like Dunkin'. So in the numerator, it's the number of kids, number of people that are kids and they like Dunkin', divided by the number of people that fit into this condition. So the number that like Dunkin'. So scrolling all the way back up, I've narrowed myself down to just working with this data as I know they prefer Dunkin'. So in total, I have 110 people. From that, 60 of them are kids. So this is going to be 60 out of 110. Okay. And to simplify, these are both divisible by 10. So you have a 6 out of 11 chance of this occurring. And so we'll do one more. We'll do the reverse of this. We'll determine the probability the person is a kid, given they prefer Starbucks. So again, our probability of selecting a kid, given they prefer Starbucks. In the denominator, I now am narrowing it down to just the people that like Starbucks. And then in the numerator, it's that overlap, the number of kids that prefer Starbucks. Okay. Scrolling back up one last time. They prefer Starbucks. There's 115 people in total. 40 of them are kids. So I have a 40 out of 115 chance. And then we can simplify it. These are both divisible by 5. So that leaves us with 8 over 45. And that's as simplified as we can go. Okay. All right. So I just have one more example. Okay. And then that will be it for this section as well. I'm going to scroll to a new page just so it's not all cluttered. We're going to work with a hat that contains some money. A hat contains 4 bills. A $1 bill, a 5, a 10, and a 20. Each bill is equally likely to be selected. And 2 bills are selected with replacement. Okay. So we're going to bring back some of our tree diagrams. First thing we're going to do is we're going to construct a tree diagram in sample space. So we want to find all of our possible events pretty much. Okay. So in terms of the number of events, I have 4 possibilities on that first draw. Pick the bill out, put it back in. I've got 4 possibilities for the second. So in total, there will be 16 events. Okay. So drawing our tree diagram, I got 4 possibilities. So on that first draw, I could draw 1, 5, 10, or 20. Whatever that bill is, I look at it, goes right back in. So from each of these, I have 4 more possibilities. So again, I can draw a 1, a 5, a 10, or a 20. So this leads to our sample space. We can draw a 1 followed by a 1 and a 5, a 1 and a 10, a 1 and a 20. Same thing happens with 5 starting out. So I can draw a 5 first. And then I run through every possibility, a 1, a 5, a 10, a 20. Keep trekking. Now I draw 10 and I've got 4 possibilities again. So from that 10, I draw a 1, a 5, a 10, a 20. And then if I draw that 20 first, I got 4 possibilities. 1, 5, 10, and 20. So this is every possible combination for our draws. All right. So now I want to calculate some probabilities. We're going to determine the probability that first, both bills are $1. Okay. So out of my 16 events, I have a single one where both of them are $1. So the probability of selecting $1 and $1 is 1 out of 16. And again, you can use that end we just did in the last section. Probability of getting 1 on the first draw, 1/4. One probability of getting a 1 on the second draw is 1 out of 4. So 1/4 times 1/4 gives you 1 over 16. Okay. Now, we want to determine the probability, probably do this on the next page, that both bills are $1, given the first bill selected was $1. Okay. So I've got this new condition now. Going back up to our lovely tree diagram, my first bill is $1. So all of these options are gone. I selected the one first. So I've now narrowed it down to 4 options. From those 4 options, one of them lands me with $1 and $1. Okay. So instead of having a 1 in 16 chance, because you selected a $1 bill the first time, you have a 1 in 4 chance. So for this conditional probability of selecting $1, given you did select $1 on that first bill, is we've narrowed it down to the options that select a $1 bill first. Out of here. Then we want to see from those, what's the probability or the number of events that give you $1 and $1. So 4 options result in us landing a $1 bill in the first draw. From those 4 options, one of them fits this criteria. So these are my 4 possibilities. And from the 4, just the single one satisfies them both being $1. And the final one we're going to do is determine the probability that both bills have a value greater than 5 if the first bill selected is a 10. Okay. So ultimately what we're looking at is the probability we get something greater than 5 given a 10 was selected first. Okay. Going back up to our chart, I have selected a 10. So this narrows it down to 4 possibilities. Okay. I've got 4 events where a 10 is selected first. From a 4, just these 2 give me a second bill that is also greater than 10. So really, out of these 4 possibilities with a 10 being drawn first, 2 of them fit that criteria. So you have a 50-50 chance of selecting 2 bills greater than $5 in value.